Awesome. Hello. Welcome to the second half of the Global AI Student Conference. My name is Loxley.
And the normal staff are muted here. My name is Dawood Idris, and I'm so happy to join Loxley on this session. Hey, how are you doing?
We have an amazing set of talks coming up. So whether you've been watching this entire time or just joining now, this is going to be an absolutely amazing second half of the event. And first of all, Project 15. I literally just learned about Project 15 this last Thursday on Earth Day, and I think it actually is a fantastic segue into our next talk, where we're welcoming Raghav Rawat with his talk on acknowledging Edge AI and its fantastic applications. So, Raghav, welcome. Thank you so much for coming on. From what I've heard, you have experience in machine learning, deep learning, and even some quantum computing, which I am personally super excited about. Would you like to give us a little more about yourself and your interests before you dive into your talk today?
Yeah, thank you, Loxley and Daud, for having me here. I'm really happy to be here. And I am from India, and I'm a Microsoft Learn Student Ambassador for almost about 8 months now. And I have been learning about machine learning, deep learning throughout my college years. I'm a pre-final undergraduate at the moment. And I'm really happy that the video about Project 15 was just shown, and would like to continue about it. So
awesome.
I'll start with my screen share.
Yes, of course. We are super excited to hop into that.
Yeah, I hope it should be visible now.
Yes, we can see it.
Okay. Yeah. So hi, everyone. This is Raghav. I'm going to be talking about Edge AI and its fantastic applications. And so hope you have enjoyed all the sessions up till now, and you'll be enjoying mine as well. So the points of discussion for my session would be introduction to Edge AI and how it is a culmination of the two broad fields of edge computing and artificial intelligence. I'll be moving on with the genesis of tiny machine learning for Edge AI, and then model diagnostics and features. So there are some certain added special features onto that we employ on edge devices in order to let the machine learning and deep learning models to be able to run effectively on the resource constrained hardware. So I'm going to be talking about it in a minute. So I'll be moving on with the edge machine learning model topologies. So these are the custom models which we can try to inculcate within the deep learning frameworks. And it is sort of a demo that I would be giving of a project that I have implemented. And I hope you'll like that. I'll then be moving to Lite. TensorFlow Lite is one of the most popular frameworks for edge devices, following like in expansion to TensorFlow, and how you can convert your already trained and deployed models for full-fledged AI systems into edge devices. I'll be concluding my session with real-life applications of Edge AI and how it can be of boon to both the fields of edge computing as well as artificial intelligence. Yeah. So Edge AI, yeah. So edge computing has been a field of a long time now, and we see a lot of microcontrollers and microprocessors being used in our daily lives. And artificial intelligence obviously is like a buzzword of the decade. So everyone is wanting to learn about artificial intelligence, and definitely it's very interesting and intriguing. So regarding edge computing, we have been seeing edge devices and microcontrollers specifically for a long time now, and they started with the circuits and relays as their integral components. But today, as throughout the years, we have seen the more dominant aspect for the edge devices have been the programmable components. That is the software side of the microcontrollers, and this sort of enables the devices to give more functionality, and also it directly enables to get us more services for less amount of compute power. And yeah, that is the power of software over hardware. And deep learning, the heart of artificial intelligence, has been a bit of a revolution already. So it has given to us some amazing artifacts like object detection, natural language processing, speech synthesis, and it has given rise to some amazing areas of research like computer vision, human-computer interaction, and AI chatbots, robotics, and whatnot. So what I'm trying to emphasize here is we can train these deep learning models on our full-fledged systems, such as laptops and computers. But I hope you wouldn't be ready to take up your bigger systems like laptops and then go to the object. For example, if you want to do object detection, I hope you won't be wanting to take your laptop cameras and go to the setup where you are interested to do the object classification. So in order to do that and have a good experience out of it is to have smaller devices running those algorithms. And that is effectively what edge AI is. So this is what I want to convey today is how we can leverage the power of deep learning over microcontroller units. And for that purpose, we have a lot of good MCUs already, which are actually having host operating systems also, for example, Raspberry Pi, Arduino, and others, to name a few. So I would like to convey today the magic that tiny machine learning entails, and I would like to, hopefully you'll be enjoying it. So the genesis of tiny machine learning for edge AI, this started with the big names such as Microsoft and Google. And yes, one of the most popular applications of edge AI is the virtual assistants itself. And the task of wake work detection, it was achieved by these big names in the field. And how they did that was, inculcate smaller microchips which were dedicated to reacting to the certain wake word, and using that wake word they were able to give quick responses through always on neural networks. So yes, this is the underlining point here. We require always on neural networks into our edge devices. And what was the use of this after all? So these companies wanted to give extra services and a certain user experience onto mobile applications. And thus, so what I'm trying to emphasize is the smaller we go, as we try to compress the models, they take up less computation power, and which is of immense importance when we talk about edge devices and IoT devices. So that is how using a specific and focused microchip, the applications of such applications were able to be employed on smartphones. So yes, when we want to deploy our deep learning and machine learning models onto edge devices, there are certain factors that we need to consider. And there are actually pretty important features without ensuring the AI edge AI system would be falling apart. So what are those features? So yes, energy is one of the most important feature. To give it into an example, many of you would be using smartwatches, such as Apple Watch or some Android-based watch. And so how many of you would like to have a watch which needs charging every other day? Or would you rather prefer a watch that in a full battery backup runs over a month? Yeah, so everyone would like to go for the second option. So yeah, energy is definitely of immense importance. And to validate that, I have got to use some statistics from Cambridge University Press. The display, this is the statistics of average power consumption for parts of smartphones. So the display uses 400 milliwatts on average, Bluetooth uses 100, accelerometer uses 20, gyroscope uses 130, and GPS uses about 170 milliwatts. So you can see here that the display and GPS uses the most amount of power, and sensors and CPUs do not tend to use so much power. So effectively, what deep learning computation requires is the CPU, and the collection of data is done through the sensors. So that is how we can actually inculcate something like edge AI, and which is actually implemented already. So some important features of these type of algorithms running on the edge are they are lightweight. First of all, they involve low latency. So obviously we can't use a model that is waiting for a cycle through the cloud. So some sort of cloud service which is hosting the data and the model itself. So that would be very much time consuming. We need something on the edge that that hosts the model and computes the data. And with this, I'll follow up to my next point, which is privacy. Since the data is right there on the edge and the model as well is right there on the edge, we can enforce a better layer of privacy for the users, and that would ultimately build up more trust on the products. Less power consumption is definitely the important point. Efficient models are thus required for better computation and deployment of such type of models, or even pre-trained models for the concern. So some of the state-of-the-art models that we have seen throughout the years include the MobileNet V2 architecture. This has a MobileNet-based network and an SSD network, and in the middle it runs through a bottleneck architecture. So what the important feature about it is this is a pretty lightweight model, and and it is one of the state-of-the-art for object detection, and it is easily available as a class through TensorFlow API, and you just need to import it, and it's as easy as that. Some important models include the LSTMs for sequence models and the convolutional nets. So for sequence problems such as natural language translation or speech synthesis, you have LSTMs. For object detection and other important pattern recognition tasks, you have convnets. But they come with their own restriction. That is, they are pretty huge in size, and they inculcate a large number of parameters. So I want to introduce a sort of a new approach to this. So another model, which I would call tiny models. So I would like to introduce the fast GRNN, which is introduced by Microsoft in the year 2018. So fast GRNN stands for fast, accurate, stable, and tiny gated recurrent neural network. So and might be a little overwhelming to see, but I'll try to give it through a project that I have implemented, so you'll be better able to understand the intuition behind. So this model also follows the general recurrent neural network structure. So that this has an input port and has an output port for each cell unit, and it has a hidden running cell state within. And it has a couple of UNW matrices, which are the learning matrices for each cell. And how it is able to, reduce the size and improve the accuracy is that it uses certain repetitive residual connections. So for each cell unit, we are trying to reutilize the learning parameters instead of initiating new ones, so as to make it a cyclic pattern to learn new sequence data. And that is how this model is able to reduce the size manyfold. So the application that I have introduced is that of a sound recognition, and what I'm trying to do is do the feature extraction from the audio data. So we do something called as MFCC computation, because of which we are able to get the amplitudes of the audio data into numerical data. So this is the pre-processing part. And then we feed it to the neural network, which would be the fast GRNN in this case. And this, after training, we give the weighted parameters to our testing channel, where we take up unknown recordings. We do the MFCC computation and do the inference. So this is the pre-processing pipeline, which I have just given here to ensure there's no gap in the understanding. Here, I'm just taking an audio data for a dog barking. So this is the time series data. This is the frequency spectrum. This is the frequency spectrum in decibels. And the final one is the MFCC computation. And this sort of pattern you can see is basically what is ultimately converted into numerical data for computation in the neural network model. So these were the model summary for my trained model, and on the right you can see the model training. with the help of early stopping, it was able to actually achieve, the state of the art performance. And yeah, this is the statistics for that. Okay, I'm sorry. I'll be covering the comparative analysis. So what this model has returned to us after training is the different parameters as NumPy files. So how this model is much faster is that it directly computes on the NumPy data, and it is able to take up the NumPy data and then load it again, and we can directly use the mathematical formulas which I had shown previously, formulas, and we can do the computation through the trained parameters directly. So using mathematical equations, the process becomes much faster. And you can see here in the bottom picture that the model size at the end was just 4.8 kbs. And the number of I'm sorry, and the number of parameters that we trained was just 1230. So the in-depth comparative analysis is as follows. I was able to train the fast GRN model with the accuracy of 87.89%, which is just about 1 or 2% less than the other state of the art. And this had a reduction in the parameters by a huge amount, as well as the final trained model size. And these results are just astonishing. And thus, we can conclude that these type of models are the ones that can be actually efficient for the edge devices. So talking about how these deep learning models and algorithms can be configured in order to get something that would be better off for edge devices where the resources are much more constrained. So the first thing I would like to talk about is quantization. It is a very well-known concept when we have to compress the model and the computation requirements. And I'll introduce it with respect to TensorFlow Lite. So because it is one of the most popular frameworks. In quantization, what we do is we restrict the decimal precision accuracy of the weights and biases of the basic neural networks, because of which we directly reduce the amount of time required for computation as well as for accessing those values, because when we have bigger values, we require more time. If we have restricted decimal numbers, we won't require much time to access. So that is how we work both on our memory as well as the speed. Pruning can be related through the dropout feature of neural networks, and on the right is the representation for pruning. Then we have custom model topologies, which, for example, the fast GRNN itself, which can be used for efficient tensor decompositions and distillation. So the idea behind this is using some certain, beginning with some certain models, because of which at the end we'll be having much smaller trained models and less number of parameters. Apart from that, TensorFlow Lite provides us with some amazing special purpose hardware accelerators. And these can be of the form of software as well as hardware. For software, we have Android-based neural network APIs, and for hardware, we have edge TPUs, GPUs, and also something called as GPU delegates, which is a good feature to try out your model for different configurations of GPUs. So what are the benefits of quantizing? So all the CPUs are supported for quantization, as it's a mathematical manipulation. So independent of your operating system, your platform, or whatever you're working on, you can always do quantization. We have reduced latency and inference costs for obvious reasons that our data is smaller, and obviously we are not very much worried about the accuracy for edge devices. What we need to do is to get up and get a certain functionality running. So for the same purpose, we require reduced latency, and accuracy is not our prime concern here, because we are getting immense and many-fold increase in the trained time. Sorry, reduction in the trained time and the model size. So yeah, and then we have low memory access cost and usage. And also it allows for execution on fixed point operations for restricted and optimized hardware. So yeah, so when we talk about edge devices, they are having just a few kilobytes in their cache, and for the main memory they have some megabytes. And in the case of full-fledged systems that we use, we are having RAMs of gigabytes and memories of in terabytes maybe. So that is the reason behind doing all these techniques, to actually enable deep learning algorithms to be run on edge devices as well. So the TF-Lite workflow is as follows. It is divided into two parts: converter and interpreter. So what is the work of converter? It transforms TensorFlow models into a form efficient for reading and interpretation by the interpreter. It introduces optimizations to improve the binary size model. So we are not dealing with the full floating point numbers now. We are dealing with the binary size models, and thus the reduction in the model size. The interpreter is a diverse platform. So whether you are on Android, iOS, embedded Linux, whatever for that matter, it is able to compile the model and run it and make the inferences. And it also provides platform APIs for accelerated inference. So the workflow is as follows. You can use your pre-trained or retrained models. TF-Lite also provides you the support for custom models, so you can develop and deploy your own custom models. And yeah, moving on with the performance. So it provides to you directly the support for validating and accelerating models using the GPU delegates and the neural network APIs again. And by the end, you can optimize your model using the optimization toolkit, deploy it, and you're good to go. But why go for edge AI? So we know that CPUs and sensors use negligible power that I have already discussed. And compared to radios and displays, it's just very negligible. So you can say that in order to collect data, we have sensors. They are like the open nodes to the world. And for the computation, we have CPUs. So this enables us to work a bit on our models and actually make them feasible to be run on these type of CPUs, which have some constraints on their resources. And yeah, we capture more sensor data than we actually use. So often there are constraints on the bandwidth. Talking about computer vision applications, we have bandwidth constraints or some other speech synthesis. We have a lot of constraints, as well as battery constraints and power requirements. But the sensors are always on. So that's why we are capturing data at all times, but we are not probably using it to the full extent. Deep learning is compute bound. This is my personal favorite. So deep learning, what does it do? It takes up matrices and it does the matrix multiplications to get the final computation. And to do these matrix multiplications, it requires to take up the data from the memory. These are the only two tasks that deep learning is achieving. And by doing this, we are getting some amazing artifacts out of it. So the only restriction is on the compute, and it's not on the memory, and that's why deep learning is more can be worked upon for better utility of the CPUs of edge devices. Deep learning is actually very energy efficient. So for this, I have an example. So the operations of deep learning are calculated using a metric which is picojoules per operation. So roughly, if we take about 5 picojoules per operation, and the mobile net takes up about 22 million operations for a task of object detection. So even using the mobile net for a deep learning algorithm like object detection, we are just using 110 microjoules of energy. And even if we use a button cell for this particular task, it can do that task for more than a year. For if each of that computation is taking just this amount of energy. Deep learning makes the most sense out of the data. That is for sure. In the applications of computer vision and pattern recognition, deep learning is proved to be the most superficial. And we have faster inferencing straight at the edge. So this promotes for the privacy, as well as lower latency, which are the prime concerns for edge devices. So some amazing applications of edge AI. We have Envision glasses. This is already a product in the market, and you can call them as EDEP glasses from Spider-Man Far From Home. But jokes apart, these glasses are going by the Microsoft's motto of responsible AI and inclusive AI. These are some amazing product that enforces empowers people with disabilities to have normal life in their workplaces and on general society setups. So then we have smart detectors for hazardous setups. These type of edge devices are able to do the computation much faster and with low latency, which makes them optimum for some critical setups. We have crop yield and pests detection. This is actually being implemented using unmanned aerial vehicles and drones. Then we have privacy and fostering privacy at the edge. And this you can say you can convey it using the new field of federated learning. I hope a lot of you might be knowing about. So this is also an interesting application for edge AI. I've put down some important resources to learn more, and I have